Complex zeros. What's a complex number?
I'm not about to answer this, but I was. But...
Come on, y'all.
All right, give us a hint.
-1.
All right, a complex number is made up of two parts. It's got an imaginary part and a real number part. Remember?
Like
so, yeah, well, like 2 plus 3i would be a complex number, right? So, when we talk about zeros, we've talked a lot about polynomials and their zeros. And zeros happen where? Where the graph does what? Crosses the x-axis. Algebraically, how do we find the zeros? Solve it for what? When it equals what? 0. And how do we solve it for x when it equals 0? What have we been doing? Factor, and we set each piece to 0, right? And sometimes we use the quadratic formula, and sometimes we get these imaginary numbers. And the good thing about this lesson today is I kind of took you, I didn't make you do just real numbers when we were doing just real numbers in the book. We did all zeros instead of just real number zeros. So this will be kind of a recap for you, which is a good thing. All right, when...
Jackson, you see him?
All right, tell me this. When you have a polynomial. Oh, my goodness. How many zeros does this polynomial have?
5.
How do you know? Close. The degree. The degree tells you how many zeros. Now, here's the thing about it. This is the degree. It equals the number of zeros. Remember, before I told you it has no more than that many real zeros, okay? But it has exactly that many zeros, and that includes imaginary and real numbers, okay? So we're now including everything, what you see and what you don't see. This could include repeated zeros, though, okay? So if I have something like x plus 1 times x plus 1 times x minus 4, okay, then you see how this x equals -1? If I solve that, come on, don't do this today. Happens twice, right? That's a repeated zero, but it still counts as 2 of my zeros towards that maximum, or towards that n number of zeros. Does that make sense to you? Your degree equals your number of zeros. That is called the fundamental theorem of algebra. Everybody okay on that? Like I said, we covered that. We talked about it. Let's see. We also talked about, well, actually, let's just look at this example. Right? You need me to go back? Tell me this. How many zeros does this function have? 3. 3. How do I know? How do I know that this has 3 zeros? Come on, y'all, you can do this. I know it's early. I know it's Monday.
-3, 1.
How do you know that, though? Because whenever we solve, we do what? You're right. Put it equal to 0, right? So we know that the number of factors, like this, tells me the number of zeros, right? Right.
Yeah.
What, without actually going through this, what would the degree of this polynomial be? Without actually foiling it out, multiplying it out. If it has 3 zeros, then it must have a degree of 3. All right, what are the zeros here? That's exactly right, -2i, which is my imaginary number, and that is A-okay. All right. What if I asked you to put that in standard form?
I would not do it. You would foil it.
You would foil it. So, y'all are such jokesters this morning. So whenever I FOIL something that looks like this, and let me just go to a new slide so you can see. X plus 3, x minus 1, x plus 2i. Tell me how I FOIL something like that. There's 3 pieces.
You got it, yeah.
You can't do more than 2 at a time. So as you multiply out, you're going to do the first 2, then take it to the third. So do it with me. X times x is... Mm-hmm. Mm-hmm.
3x.
Mm-hmm. Clean it up a little bit. What's it look like? Minus 3. That's exactly right. Now I need to take it to this one. So I have x plus 2i. So how am I going to multiply that through?
How do you mix up a square number?
I think I just missed this one. It's okay. Keep going.
X cubed plus 2y squared. 2x squared. 4x.
If you had one like, and again, that's my fault. I shouldn't have used the one that I. Let's make this. Sorry. X minus 2i. X plus 2i. How many zeros? 2. How many real zeros? None. Both zeros are going to be imaginary, right? What would this look like in standard form? Mm-hmm. Go ahead. 2ix minus 4i squared. What happens with I squared? It becomes a positive. That's exactly right. So this becomes plus 4, right? These are exactly the same but opposite signs. So what happens with those? They cancel out. So, that's exactly right. Could you look at the original equation and tell that that had a degree of 2? Yes, because it's got 2 factors, right? Graphically, 2 factors, 2 sets of parentheses here. This is what we started with. We FOILed it out to get here. We're just kind of, yeah. Sorry.
What happened to this?
We're done. It's done. That's all. Yeah. I'm just helping you through foiling it out some and getting it in standard form. This is a lot of repeat. That's why I'm not doing it quite so formally. It's a lot of repeat of what we've already done in chapter 2. We're just adding imaginaries in there is really what we're doing. Graphically, if it doesn't have any real zeros and it's a power of 2, it's a degree of 2, what does that look like? It's a parabola. What's special about the parabola, though? It doesn't cross the x-axis. That's exactly right. And it is going up. So, and it's got a y-intercept of what? 4. It's going to do something like this. Because the solutions are imaginary. The zeros are imaginary. Does that make sense? Okay. See how we're kind of pulling everything together?
Okay, explain one more time.
Okay.
I see how the 2's cancel out. How did that 4 cancel out?
Well, the 4 didn't cancel out. Negative 4i squared.
I'm listening to her talk and I'm writing at the same time. And
It's okay.
I feel like
I squared is the same thing as negative 1, right? So negative 4 times negative 1 is positive 4. Essentially, anytime I squared is hooked to a number, you drop it off and you change the sign of the number. So it didn't really cancel out. I just changed it to plus 4 instead of negative 4i squared. That plus 4 is coming from the negative 4i squared. This is where I FOILed it out. So it was x times x is x squared. This one here. And then minus 2ix comes in here. And then negative 4i squared. Can you have a mixture of real and imaginary solutions? Yes, sure you can. Sure you can. What if it... What if it looked like this? How many solutions? 3, right? There's going to be 3 zeros. How many real zeros? Only 1. 2 of them are imaginary. What is the degree here? 3, right? So if you think about it graphically, I know one of the zeros is what? What's the real zero here? 5. 1, 2, 3, 4, 5. So maybe it does something like, without actually multiplying it out, is this a cubic? Something like this? Okay. See how this one only has 1 real zero even though it's a cubic? Okay. Which brings me to the next thing I wanted to tell you about. And we've talked about this too, every odd degree polynomial has at least 1 zero. Why? Why might every odd degreed polynomial always have at least 1 real zero? Because why? Why do the even ones not have to have 1? Look at that quadratic we had before. A real zero looks like what on the graph? Huh? A parabola. And a parabola does what? Both ends do what? They go in the same direction, right? Every even degreed polynomial, we talked about this within behavior, goes off in the same direction. So it's possible for it to never do what? Have a zero, which means cross the x-axis, right? But if an odd function, if you graph an odd function, what happens on the ends of odds? They're opposites, right? There's no way you can go forever in opposite directions and never cross the x-axis. Does that make sense?
Yeah.
No matter what else, sometime you have to cross. Now you might cross more than once, but you have to cross at least 1 time, and this cubic is an example of that. Does that make sense to you all? Okay. Oh my goodness. Let's see. Let's do this. Take it a step further. I should probably be titling these for you. Writing an equation with given zeros. So let's say I have this polynomial, and I told you that I know that -3, 4, and 2 minus I are zeros of the function. How might you write an equation of the function? X what? Plus 3. Go back to the last chapter we did. Okay, if we have a 0, we also have a, starts with an F, factor. If we have a 0, we have a factor, right? If we have a factor, we have a 0. We can work both ways. We're kind of going backwards now. If I know that x equals 3 is a 0, then what must that factor be? X plus 3. That's exactly right. We have to change that sign. And if I know that x equals 4 is a 0, then what's the factor? Good job. Now here's where it kind of gets a little tricky. What is it? X what? Minus the 0. What's the 0? Is that it? Here's what you also need to know. You might think that that's it. Real zeros are easy to do. Okay? But whenever I have imaginary, and this is called the complex conjugate zeros theorem, which is a big fancy word, you don't have to know the name of it. If you have a polynomial that has a real number coefficient, okay, then if a plus bi or 2 minus I, if you have a complex number that is a 0, then you also have to include the conjugate of that. Okay, so anytime you have imaginaries or complex numbers, you have to include both. So what I have to do is say, okay, well then if this is a 0, I also have to include Does that make sense to you? Because that is also a 0. If you're given one complex 0, you have to include the conjugate of that complex 0 also. Okay? And we're not going to have imaginary numbers in our equation whenever we actually write the equation. And including the conjugate gets those imaginaries out of there. If you think back to Algebra 2 when you were rationalizing denominators. I know that this is, some of y'all are looking at me with spaced looks on your faces. We'll do one more example after this. To help you out. All right, let's see. Nothing to it but to start foiling out. I would actually, let's see. Well, I guess that one's good. All right, here, what do we get? X squared minus 4x plus 3x minus 12. Now, what I'm going to do, it is easier if you multiply the conjugates together also, and then we take the first polynomial times those conjugates multiplied together. And I'm going to leave them kind of chunked together exactly the way that they are, okay? And watch what I mean by that. What do you get here? X squared minus x times 2 plus I, right? Yeah, it's nasty. All right, let's clean up the first one. That one's easy. X squared minus x minus 12.